Welcome to this explainer. Today, we're taking a really deep dive, a macro to micro journey, really, into deep space to solve a pretty fascinating cosmic mystery. We are looking at a galaxy that, by all conventional measures, has been dead for billions of years. Seriously, to the casual observer, there is absolutely nothing going on here. Yet, by zooming all the way in on the faint glimmer of its oldest, most elusive stars, astrophysicists have actually managed to resurrect its entire life story from the dark. It is a brilliant piece of cosmic forensics, and we're going to break down exactly how it's all done. So let's put on our detective hats for a second. How exactly do scientists age a seemingly dead galaxy? I mean, think about how a typical galaxy works. When it's active and forming stars, it's rich in gas and dust. Those are the fundamental raw materials of cosmic creation, right? The fuel for the stellar engines. But when those materials are entirely stripped away or used up, the galaxy just goes quiet. It completely stops producing new stars. So the core question driving our whole investigation today is this: how in the world do we read the history of a place where absolutely nothing new has happened in eons? Well, first things first, we gotta understand the scene of the crime. We're investigating a specific classification of celestial object known as a dwarf spheroidal galaxy, or DSF for short. If you're looking for action, trust me, this isn't it. These are some of the absolute quietest, emptiest corners of our entire universe. They are low luminosity, low mass, roughly spherical in shape, and most importantly for our mystery, they are completely devoid of the interstellar gas and dust needed to birth new stars. They are, essentially, galactic graveyards, just floating out in the void. And our prime suspects for this investigation? Meet Caldwell 17, which is also known as NGC 147. Located way out in the Cassiopeia constellation, it's sitting about 2.58 million light-years away from us. It exists as a dwarf spheroidal satellite, which means it's gravitationally locked in an orbit around our massive galactic neighbor, Messier 31. You probably know it better as Andromeda. When astronomers point their instruments at Caldwell 17, observations show a complete and total deficit of the hydrogen gas required for star formation. There's no stellar nursery here. This specific galaxy has been entirely inactive for a very, very long time. Since there's no swirling gas left to study and no newborn stars lighting up the darkness, astrophysicists are forced to get creative. They treat the existing, aging stars as a literal fossil record. It's exactly like how a paleontologist uses ancient calcified bones to reconstruct the biology of a dinosaur. Astronomers have to mine the ancient stellar populations of satellite galaxies like Caldwell 17. By digging through this luminous fossil record, they can reconstruct its ancient past and finally understand how violent interactions with larger companions, like the massive Andromeda galaxy, actively shaped its evolution and ultimately its demise. To actually read this fossil record, we rely on a very specific type of pulsating star called an RR Lyrae variable. These stars are incredibly special to astronomers because they act precisely like ancient cosmic clocks. But why does finding one mean the galaxy is so old? Well, RR Lyrae stars are relatively low-mass stars that have entirely evolved off the main sequence of their lifespans. They're now in a phase where they are burning helium in their cores. Because they're relatively small and burn fuel at such a specific rate, it takes them over 10 billion years just to reach this specific pulsating stage of their life cycle. So finding even one of these variable stars out there is an absolute ironclad guarantee of extreme age. And what's super cool is that these cosmic clocks actually have two distinct heartbeats that astronomers look for, categorized by the unique rhythms of their changing brightness. First, we have the Bailey-Ebb type. These are fundamental mode pulsators with a sawtooth asymmetrical light curve, meaning their brightness ramps up sharply and fades slowly, with periods lasting anywhere from half a day to about 1.2 days. Then we have the C-type. These are first overtone pulsators featuring smoother, much more uniform sinusoidal light curves and shorter periods, pulsing in under half a day. By measuring these very distinct, reliable pulses, astronomers can decode the star's exact properties and confirm, yep, that is definitely an ancient RR Lyrae. But finding these stars is a painstakingly difficult process. Because these objects are incredibly faint and sitting 2.58 million light-years away from our telescopes, earlier ground-based observations really struggled. Atmospheric interference and errors just heavily blurred the results. So to solve this, scientists turned to deep archival data from the Hubble Space Telescope. They literally took the actual pixel variations in brightness over time and mapped them onto expected light curve templates using some intensely complex custom algorithms. It's just an extraordinary feat of engineering and math, essentially pulling the faintest, most rhythmic signal out of an ocean of cosmic noise. And the crucial takeaway from all this painstaking searching: despite the immense challenges in measuring their exact pulsating periods from millions of light years away, simply confirming the existence of these RR Lyrae variables is undeniable proof that Caldwell 17 contains a stellar population at least 10 billion years old. Just let the magnitude of that number sink in for a second. This dwarf galaxy might be a dead, quiet ghost town right now, but these flickering clocks prove its foundations were laid down in the very early days of the universe, shortly after the Big Bang itself. But hey, any good detective knows that a single piece of evidence, no matter how compelling it is, just isn't enough to close the case. You always have to corroborate your findings, right? If Caldwell 17 really is dominated by a population that formed 10 billion years ago, there should be other, totally distinct chemical fingerprints left behind in the galaxy. So we have to ask, how can we confirm this ancient timeline using a completely different scientific method just to ensure our cosmic clocks aren't somehow misleading us? To cross-reference the age, we turn to something called metallicity. Now, in the field of astronomy, it's a little quirky. Basically, any element heavier than hydrogen and helium is simply considered a metal. By looking at the iron abundance in the stars, we can reveal the entire chemical enrichment history of the galaxy. Older, earlier generations of stars tend to be incredibly metal poor, mostly because the universe just hadn't created heavy elements yet. Conversely, newer stars, which are formed from the recycled, exploded remnants of dead stars, are much more metal-rich, so the amount of iron acts as a brilliant secondary timestamp. To be absolutely certain of Caldwell 17's metallicity, scientists use two very different detective lenses. First, they use the Palomar Cosmic Web Imager to look at integrated light spectroscopy, which essentially captures the combined glow of the galaxy's entire central region all at once. Then, they compared it to resolved stellar measurements, which involves zooming all the way in to look at the chemical makeup of individual red giant stars. And incredibly, the measurements matched up perfectly, within a microscopic margin of less than 0.1 dex, which is the logarithmic unit astronomers use to measure chemical abundance. This tight match proves our chemical readings are highly accurate and definitely aren't just a fluke of the measurement technique. So whether scientists apply simple stellar population models to the whole galaxy or analyze that individual resolved star data, the moderately metal-poor reality of this galaxy remains wonderfully consistent across the board. It sits comfortably at an iron abundance of roughly -1. And honestly, this chemical makeup is the absolute smoking gun. It aligns perfectly with an old stellar population that had a very, very limited window to recycle its gases before its engines shut down entirely. The chemical fingerprint perfectly matches the timeline given to us by our pulsating cosmic clocks. Okay, let's piece this whole galactic biography together. This evidence strongly points to what we call an outside-in formation. Over 10 billion years ago, initial star formation triggered out in the outer fringes of Caldwell 17. As the galaxy aged, that star formation retreated inward, leaving the central core with an average age of about 8 billion years. Finally, between 1 and 3 billion years ago, the galaxy just got way too close to Andromeda. Through gravitational tidal stripping and ram pressure, which is essentially the violent process of having its gas forcefully blown away as it plowed through intergalactic space, its remaining fuel was completely stolen, and star formation ceased entirely. Yet, even with its star-forming days long behind it, Caldwell 17 holds one more truly mind-bending secret. When astronomers examine the internal dynamics, specifically looking at how fast those dead stars are moving, they calculated the galaxy's mass-to-light ratio. And what they found is wild. The visible, luminous matter, these ancient fossilized stars we've been tracking, only accounts for half of the galaxy's actual mass. The other 50%, it consists of entirely invisible dark matter. It's like this spooky, silent scaffold holding the remains of this dead galaxy together in the dark. So, as we wrap up this explainer, it leaves us with a lingering, pretty beautiful mystery. By simply observing the subtle light curves of RR Lyrae variables and the iron content of a few red giants, we managed to resurrect the entire 10 billion year biography of Caldwell 17. If we can read all of that vibrant history from just a flickering star in a seemingly dead galaxy, what other unseen, ancient stories are hiding right in the darkness of our local group, just waiting for the right cosmic detective to come along?